Hi, this is Matthew Sherland, and this is my video description for the Simulink PV array, boost converter, and grid-tied inverter model. The array itself consists of 96 cells per module. Each string has 5 of those modules in series, and the total array has 66 of those strings in parallel. The array experiences varying irradiance and temperature. These top two graphs are the waveforms of the irradiance and temperature. Irradiance begins at 1,000 watts per meter squared, decreases down to 250, increases back up to 1,000. As irradiance decreases, there would be a decrease in the current, and as it increases, the current would go back up. The temperature begins at 25 degrees Celsius and increases to 50 degrees Celsius. As the temperature increases for the solar module, there would be a decrease in the voltage. We can see it here, but specs for our array at 1,000 watts per meter squared and 25 degrees, we're seeing around 100.7 kilowatts and 273 volts. However, as the temperature increases, there's a decrease in power down to 92.9, as well as a decrease in voltage to 250.2. Currently, it's displaying the results at the end of the experiment at 1,050 degrees, and we can see that the voltage decreased to 251.5, and the power has decreased from 92.89. Now, this PV array feeds into our boost converter here, which bumps up the voltage to 500 volts. The frequency at which the switch for it operates at 5 kilohertz. Now, in order to bump it up from around 250 to around 500 volts, that would require a duty cycle around 0.5. That's because VO over VS is equal to 1 divided by 1 minus D for boost converters. And we can see it here by the waveform of the duty cycle. At this end of the simulation, it is around 0.5. This boost converter consists of a 100 microfarad capacitor in parallel before it, as well as two 12 millifarad capacitors at the end, as well as a 5 millihenry inductor. The sizes of these components are important for the ripple of the current and voltage going through the boost converter, as well as to see if it operates in discontinuous mode or in continuous mode. Now, using a scope, we can analyze that by seeing the current going through the inductor. Now it's displayed here. Now, by this, we can see that the current never dropped to zero. The lowest it goes is around 87 amps. Because it doesn't drop to zero, we can say that this boost converter operates within continuous mode. Now, the semiconductor devices that this boost converter uses is an IGBT for the switch, as well as a diode. There's one peculiar thing about these is that they were programmed to not have any forward voltage drop. Realistically, there would be some sort of voltage drop due to these components. If they were silicone, it'd be around 0.7 volts. Now, this boost converter is controlled by an MPPT controller. That controller uses the Incremental Conductance method. We can view the algorithm that it uses for this. Incremental conductance takes the current voltage, the change in current, and the change in voltage in order to compute how much it needs to change the duty cycle for each sampling period. Now, we can see at the top part here, it factors in your delta I over your delta V. Down here, it takes the average I divided by the average V. Now, it then adds these two together. So for the incremental conductance method, when your delta I over delta V is added to your I over V, if that is equal to 0, that means that your circuit is operating at the maximum power point. That would be this condition here. When it's operating at that point, you don't need to adjust the duty cycle. It's operating at the proper voltage and current. When your delta I over delta V plus I over V is greater than 0, that means you're operating at a power point left of the maximum power point on the IV curve, and thus you need to increase the voltage and adjust the duty cycle appropriately. When it's less than 0, that means you're at a point right of the maximum power point on the IV curve, and thus you need to decrease the voltage in order to get the circuit to shift left towards the maximum power point. We can see it takes those adjustments in the duty cycle, it adds those to the initial duty cycle, and that controls the pulse width modulated signal that is used to trigger the gate of the IGBT. So that was part 1 of this analysis. In part 2, I'll be going over the grid-tied inverter connected to the utility grid as well as the VSD control. Thank you.